If you recall, when we were discussing optimization over finite dimensional vector spaces, that is over the Euclidean space, we derived first order necessary conditions and then we derived certain second order conditions as well, but we didn't delve too deep into those second order conditions, saying that, well, the first order condition itself will allow you to shortlist a good many number of candidate points and then maybe just evaluate them. If there are only a handful of points, just evaluate the function at those points and decide for yourself which is doing the best. The same argument can also work, of course, for the infinite dimensional case. Nonetheless, we shall still see something about the second order conditions in this case. The reason being, the primary motivation in my opinion being, I am trying to drop some breadcrumbs towards, that will lead you towards the Pontryagin's maximum principle. Okay. Earlier we have seen that when you have this Hamiltonian, if you remember, it was dependent on x, y prime and p. Then we said that let us make this transition in our minds where we replace this with z. Yes, and in that case what we had was what was it? P times z, right, minus L itself, which was only a function of x, y and was it y prime? It was a function of z, right? So we look at it as just a function of z. Yes, and then we saw that, well, if you take the differentiation of this with respect to z, then what happens? Leads to a stationarity at z is equal to, so we saw that dh, in fact if you say that dh star, which is the h evaluated at the optimal trajectory and evaluated at z is equal to y star primed, then this was 0, right? From the definition of the momentum itself it was 0, correct? So this told us that if you think of this Hamiltonian as a function of this third argument alone, a stationary point was achieved here. Stationary point is, it could be a maxima, it could be a minima. How do we know whether it's a maxima or whether it's a minima? If you take the second derivative, you will see what happens now. See, you differentiated once, you've got rid of the z, but the p remains here. Take the second derivative, the p vanishes. Now you have to take the second partial with respect to z. So it's equal to minus L z z x y z. Now if you want to find out whether this fellow is a maxima or a minima, you have to just go ahead and evaluate this at z is equal to y star prime. So you have to actually plug in here now back z is equal to y star prime. That is, this fellow has got to be replaced by this, and hopefully you will be able to say something about the sign of this. If this fellow is negative, then at this point it is maximized. If this fellow is positive, then at this point it is minimized. So it seems like a lot rests on the sign of this object evaluated at z is equal to y star prime. Okay, we shall see by the end of this lecture that this is the really crucial detail that we will try to wrap our heads around. So our goal is to get an idea about the veracity, or at least in our minds to get a hint about the fact that this is indeed a maximization of the Hamiltonian that's happening as you choose the optimal curve. Okay, the choice variable being the y prime, which we have replaced with z. Okay, we shall see how this is so, and the tool that we shall be using for that, towards that end, is the second order condition. So you see, you have j of y plus alpha g Up until this point we have expanded only till the first term in Taylor series of alpha. Let's go ahead and expand till the second term as well. I'll just drop the arguments, just write L and the subscripts will denote the partials, because otherwise it's going to be really long. That's all, nothing else, but it's going to be really long. So this is J, yeah, J evaluated at Y plus alpha times, what was that? The first variation evaluated at Y along the direction G, which is, remember what this was? It had what all? Partial of L with respect to Y times G plus partial of L with respect to Y prime times G prime. Those are the two terms. Now if you go ahead and take the second term in the Taylor series with respect to alpha, remember, then you will have plus alpha squared by 2, factorial 2 is 2, Taylor series. So what happens then? Now you have to go ahead and take another, so that partial of L with respect to Y evaluated at x, y plus alpha g, y prime plus alpha g prime. That fellow's derivative with respect to y, that will again throw up two more terms. Do you see that initially this one had two terms, but the second term will have four terms, no? One is Ly, once it gets differentiated with respect to y, that will lead to Lyy. Once it gets differentiated with respect to y prime partial, so that is Lyy prime. The last term Ly prime, first it gets differentiated with respect to y, so you get another Lyy prime, and then it gets differentiated with respect to y prime again, so you get Ly prime y prime. Correct? That's all there is. So let's write that down. I'm not going to write the entire thing here. So when you have Lyy, remember it means the y was already existing with a g, now another g gets pulled out of this, so you get g squared. Similarly, Ly prime y prime, and you get g prime squared. Yes? What else? The other term, the cross term, is a little tricky, you have to think a bit, but not really that tricky. What comes out with the cross term? If you already started with Ly, when you take its partial with respect to y prime, g prime comes out, so it's g prime instead of g prime squared or g squared. Is everyone following this? This is just expansion in terms of alpha. Alpha appears in two of the arguments out of three, x, y and y prime, out of which x is not affected by alpha, y is affected by alpha because y gets replaced by y plus alpha g, y prime is affected by alpha because y prime becomes y prime plus alpha g prime. So every time you differentiate with respect to alpha, whatever multiplies it has to come out. Depending on whether it's g or g prime, something or the other comes out. One is already existing in the first variation, that's why it's a square. So you have plus 2 Ly y prime g prime. Of course you have to integrate this whole thing. Isn't it? Yes. So this is plus, of course, then you have these other higher order terms. Now, this we might still understand, okay, it's a pure quadratic in G prime, pure quadratic in G. It is this term that seems to bug us a little bit, but not really. Once you realize that after all this G is a vanishing perturbation, let's look at integration Ly a to b g prime, okay, let's put a 2g prime here, dx. Yes, that's that cross term. Does something occur to you when you look at this? Sorry? Yeah, so it is basically, isn't it, the derivative of g squared, Like if you take g squared d dx, then this is 2g and dg dx, which is g prime, right? So therefore d of g squared is equal to 2g g prime dx, correct? And that's what's sitting over there in that integral. So this is d of g squared. So if you do this partial, treating this as u and dv, so it's uv, so L y y prime g squared evaluated between a and b. Does it matter? It's a vanishing perturbation. So g squared at a and g squared at b are both individually 0. So this entire term vanishes. All that you are left with is minus integration a to b g squared d dx of this fellow, correct? D dx of L y y prime dx. Is that clear? Fantastic. Now then, so what we've got here, if we are allowed to classify this, and we will, this entire thing here within this blue here is nothing but the second variation. And we've already seen earlier the alpha squared is 0 here. So of course, depending on the sign of the second variation, you'll be able to tell whether it's a minima or a maxima with respect to alpha. Yeah, whether if you're moving along this direction, if you're perturbing, what should happen if it's got to be a minima? This fellow should be positive, right? Positive semi-definite at least. So you would at least expect this condition to be met. Now let's look at this term after all that manipulation that I've done in red and see what it looks like. So this fellow, of course, evaluated at y along the direction of g, is now going to be integration a to b. Look, this part remains exactly as it is, L y prime g prime squared plus there was this L y, but the other term gave something else, no, with a minus sign. So what I will have is L y minus d dx of L y prime, L y prime, this whole thing multiplied by g squared, correct, dx, agreed, correct. Let us give them names so that this fellow, which is multiplying g prime squared, we call this p of x, and this fellow which is multiplying g, we call this q of x. Now because of the smoothness, you see p of x is continuous with respect to x. What about this? Well, we still have a lot of work on our hands here. Unlike earlier during the first variation where everything got transformed in terms of this single g, and then we invoked the continuity of whatever was multiplying g and said that okay, then that fellow must be 0. That's what gave rise to the Euler-Lagrange equations in the first place. Here, just having a handle on g alone isn't good enough. We cannot say that, oh, you know, for this, these fellows have to be both positive. Maybe one of them trumps the other in certain case. So therefore, maybe one of them must be positive. Here, you see, if seemingly, if one of these fellows is negative and the other is positive, but if the positive fellow trumps the negative fellow, you might still end up having a positive variation. How are we to be assured that there cannot exist such a situation? In other words, can we say something with certainty about Px and Qs separately without thinking about G, except for imposing the condition that G is a vanishing perturbation, that is continuously differentiable, let us not impose anything else on G and see if we can, independent of our choice of G and G prime, say something about P and Q. Can we? That is the question. The only sacrosanct thing that we know about this situation is that this must be positive for all vanishing continuously differentiable perturbations. So, I am saying, let us assume the following situation. Suppose P of x is less than 0 at some x naught belonging to the interval a to b. Suppose it is possible that P, the part that is multiplying G prime squared, does happen to be negative at some point. Okay, let P x naught is equal to minus 2 beta for some positive real number beta, so that it is negative. Okay, right. So this is the probably the most negative value you can assume in that interval. Wherever it is negative among all those points, find out the most negative value of Px. And then because of the continuity, you see one moment it is negative, the next moment it cannot be positive, right? So there must exist epsilon greater than 0. So let me write the epsilon greater than 0 such that for all x belonging to x naught minus epsilon to x naught plus epsilon, P of x is still less than or equal to minus beta. Make sure that you understand what I am saying here. What's being said here? What's being said is the following: it attains a value minus 2 beta at some point. Immediately it cannot flip to a positive value. It has to go through intermediate values. So it has to go through minus beta before it can possibly go to 0. So let's say that within some small neighborhood, that fellow remains negative. Not just it remains negative, whatever negative value it assumed at x naught, it does not go beyond half that negative value. So it does not rise beyond minus beta. It stays confined between minus 2 beta and minus beta within that interval. Okay, so that's how I choose my epsilon. You can choose a smaller epsilon than that, of course it will work. So there's no restriction on how small you can make this epsilon. Once you found one epsilon, you can keep making that epsilon smaller. And that is a very crucial bit here, because what we are going to see next is this. We'll complete this maybe in the next lecture, but I'll just give you a candidate G for which this fellow still has to be positive, and I'll immediately show you that that won't be true or that won't be possible in this situation. Which means what I'll essentially show you is it is not possible for Px, irrespective of whatever G you choose, it is not possible for Px to assume negative value at any point in the entire interval from A to B. And by the same token, if that is so, then Px is exactly the negative of this. So that means this had better be negative, right? Because it's minus sign. So if this fellow is got to be positive, then this fellow has to be negative, which means that the stationary point is indeed a maximum. Okay, we'll see that. I'll just propose this function to you, and you can also work it out, but we'll complete this next day. So suppose you define it in this manner. It is sine squared pi by epsilon x minus x naught for x belonging to the interval x naught minus epsilon to x naught plus epsilon, okay, and equal to 0 for x at any other point in AB. So AB minus set minus x minus epsilon to x naught plus epsilon. Okay, if this is my G, immediately you will see that my G prime becomes sine of 2 pi by epsilon x minus x naught. Of course, I have to bring the pi by epsilon outside as well. yeah, for the same, you can fill out the same condition here and it's 0 for the same interval here. With this candidate, if you substitute, the claim is that you will be able to see that the moment Px becomes negative even momentarily in some small neighborhood around x naught, I will choose a G. Notice that this G is a vanishing perturbation, right? Because it only holds some significant value in some small little interval. Everywhere else it is 0, so at the terminals also it is 0. It is also continuously differentiable because it merges at least smoothly at the point x minus epsilon and x plus epsilon. Right, so it's a continuously differentiable function, it vanishes at its end, it's a candidate, it's a legitimate candidate for a vanishing perturbation, and if you invoke this condition here, you'll see that, bingo, this term, subject to this term remaining bounded, you will inevitably be led to the conclusion that you cannot ensure this fellow is positive, which means that in order for this fellow to be positive, no matter what G you have to have P positive, okay, or at least positive semi-definite. It cannot be negative at any point, okay, because if it is, then it will violate the second order necessary condition for this optimality, okay. So we'll complete this with this example. You can already try to work out the integration. Consider the Q to be bounded by some capital D, the mod of the Q is bounded by some capital D, and carry out this integration, and you will see this immediately follows. Okay, so we'll follow through with that derivation in the next lecture. Thank you.